Hi everyone, welcome to MLT Talk. I'm Maryam Aliakbarpour, and today I'm going to talk about testing properties of distributions with respect to differential privacy. When we want to mathematically model data, we usually see data points as random samples from an underlying distribution. In learning theory, when we work on inference or prediction tasks, we usually analyze our algorithm based on this underlying distribution. So it's a key component in our analysis. The question that I'm interested in is to understanding the properties of the underlying distribution via its sample. And property testing is essentially a framework which allows us to study this problem. To precisely define what this framework is, suppose we have an unknown distribution. We assume it's a discrete distribution on 1 to n. We receive IID samples from this distribution. We give these samples to an algorithm called tester, and we want the tester to, with high probability, let's say 90% of the time, decides whether the underlying distribution has the property pi or it is epsilon far from any distribution that has the property pi. And this notion of distance is usually total variation or L1, and sometimes it's also L2 distance as well. This is a non-parametric setting in a sense that we do not make any assumption about the class of the underlying distribution. So it's the only thing we know, it's just it's a discrete distribution. The goal in this framework is to find an algorithm that uses as few samples as possible and essentially find the optimal sample complexity. And this is a non-asymptotic setting. So for every epsilon and n, the domain size, we want to find the finite number of samples that can essentially satisfy the guarantees that we required. Several problems have been considered in this setting, like estimating support size, independence testing, and so on. We will see some of these examples. We will talk about some of these examples later. So why this framework is interesting, first of all, it allows us to verify the assumptions that some of the algorithms makes about their underlying data. So, for example, if the data assumes the underlying noise is always a uniform noise or a Gaussian noise, we can verify those assumptions. And also it could actually help us the other way around. If I have some information, if I can use property testing framework to gain some information and insight about the underlying data, it actually helps me to design algorithms that are tailored for that specific data. So in this talk, I am going to talk about a problem in property testing called testing closeness or equivalence. In the statistical field, in the statistics, it's usually called equivalence testing. And we will see how to make this tester private. So an example of this problem is that suppose we want to see if gender and income are independent from each other or not. So you can model this problem as you have samples from two different distributions, income of the women and income of men, and we want to see whether these two distributions are equal or not. So more formally, this problem is as follows. So you have two distributions. We receive IID samples from these two distributions, and we give the samples to the tester. The tester has to decide whether P and Q are equal or P and Q are epsilon far in L1 distance. So this closeness testing problem is not just one problem by itself. It's actually a key component in distribution testing. There are several other problems that either can be reduced to this problem or can be solved very closely with the closeness algorithm. So it's a very central problem in distribution testing. So for example, even some other problems, just a simpler example of this problem. For example, when we know that P is uniform, we want to just test if Q is uniform or not. Or if P is known, we exactly have the distribution P and we want to see if it's equal to distribution Q. Or you can even reduce independence problem to closeness problem. So basically, if you have two marginals, P1 and P2, testing independence is just testing the equality of two distribution P or the product of P1 and P2. Also, testing histogram and mixture testing are also relevant, which I'm not going to explain the detail here. So let's talk about differential privacy. So when we work with sensitive data, like medical data or salaries data in our example, it is important to protect the privacy of the individuals whose data is essentially under the consideration. What do we actually mean by this, by privacy? So we consider the central privacy setting. So we have a data set. We have a server that is a trusted server. So the server can access all the data points. And the server does some computational task, outputs a value, and this output now becomes public. And we want to make sure that this public value does not reveal information about the participants in the data set. So let's make it a bit more specific. If the output does not reveal information about the data set, we expect that the output does not depend on a single individual in the data set. So if I change the value of a person like Bob in the data set and change it to the value of some other person like Patrick, the output I expect to be similar. I expect it to not change drastically, basically, by this single change. To mathematically define this, we suppose we have for any possible output O, and for any two data set X and X prime that are essentially differ in one sample, we want the output of the probability of outputting O remains pretty much the same. In fact, we want it the probability to remains to change by at most e to the c factor, and you can think of this e to the c as just a factor of 1 over c, factor where c is the privacy parameter. And you should think of it as a quantity which is very close to 0. So basically, this says that the probability of outputting O remains pretty much the same. So prior to our work, the private testing in both the statistical setting and the property testing setting have been considered before, and the 3 papers prior to our work that are mostly relevant are listed below. All of them, 2 of them actually consider the closeness problem, but we kind of consider this problem from a different angle. So our result is basically privatizing one of the ways that the non-private closeness tester works. So we have many non-private closeness tester. We focused on privatizing the flattening base closeness tester. But why this specific tester is important is because it gives the optimal results even in the non-private setting. And in the private setting, it's pretty much gets the tightest result we know. And this is the only tester that we can use for reductions from other problems that gives optimal result for other problems as well. So if I don't use this tester, I cannot solve independence testing or uniformity testing optimally. So this is a key component to essentially get the private testers for other problems. And after we privatize this closeness tester, we can essentially study the reductions that can be used in this setting, in the private setting, and essentially obtain results for the other problem. And this is what we did. So besides driving besides driving a tighter result for the closeness, uniformity, and identity problem, we essentially give new private tester for closeness testing with unequal size sample. So for example, in the example that I gave before, you may not have the same number of samples from your 2 distributions. You probably have many more men employees and you have a record of salary of several men. but you may only have access to few women employee, and one of the data set could be smaller than the other. And we also consider testing independence, and all of these results are almost tight, except the red terms that you see in the slide. Most of the time, for a most interesting regime of the parameter, those terms with the red expressions are not the dominating terms. So for the most of regimes of the parameters, our algorithms are tight. So let me talk about the result, but talk about the algorithms that we used. But before that, I need to explain what is this flattening-based non-private tester, and then we can talk about how to privatize that. So the flattening-based tester basically works with the frequency of the elements in the sample set. So suppose that the numbers in the circles are your samples from the distribution, and we draw the histogram based on the frequencies of the samples, and the flattening-based tester essentially captures the difference between the two histograms we receive from P and Q. So just to clarify the notation, I will use x sub I to denote the frequency of element I. So here, element 1 is repeated twice, so x sub 1 is equal to 2. So in the first step, we drew two set of samples from P and Q. We compute the frequencies. The frequencies according to the first distribution are denoted by xi, and the frequencies according to the second distributions are denoted by yi's. And then the tester just computes the value of the statistic z, which is essentially sum of xi yi squared minus xi minus yi. So this is very similar to chi-square distance or statistic. Basically what it does is this exponent 2 essentially values the more differences more. So if we see a larger difference, we kind of notice that more essentially. And this two term at the end, minus xi minus yi, are essentially tells us we should not be very concerned about the small discrepancies, or basically one specific discrepancy, which when you have one element from with frequency 1 from according to one distribution and frequency 0 according to the other distribution, essentially this is statistic consider that as 0, as pretty much no discrepancy. Why is that the case? Essentially, I mean, it helps us to reduce the variance, but why this is important to ignore this case? It's because if you have a distribution, there might be many places that you see one, like let's say you have a bunch of elements with probability 1 over n. Of course you would see a bunch of them, right? You would see few of those elements, but it may not be, these set of elements that you're observing may not match the same set of elements you will see from the other distribution, even if they are equal. So essentially this difference is kind of natural, and we expect to see such differences even if the distributions are equal. So we kind of ignore these this difference, this tiny difference of 1 according to one distribution and 0 according to the other one. And if you use the Poissonization trick, it's not difficult to see that the expected value of this statistic is in fact the L2 norm of the L2 distance of the two distributions. After we have this expected value, you can actually see that when P and Q are equal, the expected value of z is equal to 0, and when P and Q are epsilon 1 far from each other, then the expected value of z is larger than some function of epsilon. And the only thing that we need to do in the next step is to bound the variance of the statistic z. And essentially we have to make sure that the variance, if we bound the variance, we can actually have a concentration. So we can say, okay, the expected value of z is close to, the value of z will be close to its expectation in both cases. And after that, we can just use a threshold function to distinguish between the two cases. And so if the value of the statistic is lower than the threshold, we can just accept the distribution, otherwise, or say that P and Q are equal, otherwise we just reject. So basically here, a sample complexity we need to make sure that those concentration intervals are disjoint is the number of samples we need to make that intervals disjoint is essentially n times a maximum L2 norm of the two underlying distribution divided by epsilon squared. So we don't know P and Q, so this quantity of maximum L2 norm is also unknown to us. In the best case, this quantity could be 1 over square root n, which happens for uniform distributions. And in the worst case, it can be just as bad as 1, which happens for singleton distribution. So this tester, in the worst case, has essentially sample complexity of n over epsilon squared, which is pretty bad. Or in the best case, it's a square root n divided by epsilon squared. So in the like if we don't do anything at this point, this is not the optimal tester. In fact, the optimal result for testing closeness is n to the 2/3 divided by epsilon to the 4 over 3. This is usually the dominating term. But how can we gain the optimal result according to this tester? So as we see, the sample complexity is proportional to L2 norms. So we are looking for an approach to reduce the L2 norm of the two underlying distribution. But how can we do that? There is a technique called flattening technique, which I define in a second. But basically, the goal here is to map the two distribution P and Q to two other distribution P and Q prime. And hopefully, our mapping is in such a way that P and Q prime have low L2 norm. And hopefully the L1 norm is unchanged. So we make sure that the L1 norm of the distribution remains unchanged. So if P and Q used to be equal, they will remain equal after this mapping, or if they used to be far, they will remain far afterward. So now what I can do is just to map the distribution and test P prime and Q prime instead of P and Q. And since P prime and Q prime have lower L2 norm, I can test them more efficiently. So how does this mapping essentially happen? Let's say I have a distribution P and I want to reduce the L2 norm of this distribution. So remember that the large elements essentially contribute more in the L2 norm. So if I can reduce this large elements, then the L2 norm of the distribution will be reduced. So basically, I need to detect these large elements. Here is, we just color them by purple, blue, and red. If I split these elements and instead of having one element, I essentially put several elements instead of each of them. And this new distribution is it's like more flat, that's why it's called flattening, and it has lower L2 norm. I definitely increase the number of elements, but I will make sure that I do not increase the number of elements by more than a constant factor. But how do I detect these large elements? The question, because the underlying distribution is unknown, I definitely don't know the large elements in an unknown distribution. So the way that we detect them is just by drawing samples from them. So if I draw samples from P, I actually expect the larger the probability of an element is, the more frequent it will be in my sample set. So based on the frequencies in the sample set, I will determine to split every element. So for example, here, I draw samples that are shown in the slide. I see a red element twice, and I just add that number with 1 and split my element into 3 bins. And note that this would be essentially my flattening scheme, like how I split the elements. And now if I have sample from P and want to get a sample from P prime, it's very easy. I just draw samples. I look at the number of beans that I dedicated for each element, draw a sample from P, and look at the number of beans that I dedicated for that sample, the element of that sample, and then put the sample in one of the beans uniformly at random. And this would be essentially a sample from P prime. So that's how I get samples from P and convert them to a sample from P prime. So now the testing algorithm is sort of easy. We draw a bunch of samples. So it's draw a bunch of samples to determine the flattening scheme, the splitting scheme, and map the elements, and draw a new set of samples to test, essentially using the statistics that I explained earlier, to essentially test whether P prime and Q prime are equal or not. So note that these are two disjoint samples. I do not reuse the sample, and these are two different set of samples. And let's go back to how to privatizing this sample set. So now let's think why it is hard to make a flattening-based tester private. To answer this question, I need to mention first how we want to privatize this sample, this tester. There is a mechanism in differential privacy. It's called Laplace Mechanism, which essentially can be used for privatizing every function, any function. Suppose you have a function f. You can add Laplace noise to this function, and the noisy value of the function that you get is promised to be C private. But the magnitude of the noise that you are adding depends on two things. First, the privacy parameter, which the lower this parameter is, you need to essentially add a larger noise to hide, to essentially make the value private. And the other component is the sensitivity of function f. What is the sensitivity function? It's essentially, if you consider f as a function of the data point, data sets, essentially f, the sensitivity of f is how much the value of f would change if I change one data point in the data set. So if this value is high, then it means that to hide the changes in the underlying data set, I need to add a larger noise, basically. So that's why the Laplace noise magnitude depends on delta f. So we can essentially take this mechanism and apply it directly to our problem. So we have sample x, function z, or statistic z is a function of the input x, and we just add the noise, the Laplace noise, and get a z tilde, which is a noisy version and private version of z, and we can use that as our new statistic. The problem is that when we add this Laplace noise, the concentration that we used to have previously are completely destroyed. Basically, this concentration intervals get larger, and we need many more samples essentially to make the algorithm, to make the concentration bounds small. And usually, at least for this closeness tester, it definitely makes the algorithm suboptimal if we do this. So we essentially have to think of other approaches. And I just want to show you that why this flattening-based tester needs a large noise. It's essentially because the sensitivity of the statistic will be very large. So remember that we talked about flattening samples and those samples which would determine the frequency of the beans that we would assign to each element. If I change one sample in the flattening phase, let's say from red to blue, it will completely change the splitting scheme that I have. So I used to have 2 blue elements, now I have 3. I used to have 3 red elements, now I will have 2. So any further samples that show up from blue and red, they will be assigned completely different. So when I'm trying to get converted samples from P prime and Q prime, I may end up having very different sample sets if I just change one sample in the flattening phase. And these changes essentially results in a very big difference in z, the value of z. So delta z is high, and I need to add a huge amount of noise to make this a statistic private. To solve this problem, our idea was to essentially run the algorithm multiple times and take the average result essentially. So suppose we received a sample set which is a union of the test sample and the flattening sample. We consider every partition of this union into test and flattening samples, and we compute the value of a statistic z according to this specific partition, and we we compute the average over all these partitions. And now we use this average value as the value of our statistic, and then compare it with the threshold and move on similar to the previous tester. So why does this new statistic would work? The first step is to show that this statistic z bar, which is the average statistic, is accurate. The main issue is that the previous result that we have, it indicated that with high probability that the flattening set is in such a way that the L2 norms are small. But here, we are running this algorithm for several flattening samples, and we need to show that actually that result holds even when we are working on potentially non-independent flattening sets. So that's the first difficulty that we had to overcome. The second part is that the privacy is guaranteed by the Laplace mechanism, but we still have to compute the value of the delta z. So this is essentially where the reductions come from. So for different reduction schemes from other problems, you might actually end up having different value of z. So for every problem that you want to reduce it to closeness, you need to essentially compute how that reduction would change the sensitivity of your algorithm. And this is essentially for the reduction part. And we basically were able to show that for the closeness tester, you can actually bring this down to a constant. For the independence, it wasn't a constant. It has the logarithmic factor, and you see in the sample complexity that logarithmic factor showed up. And at the end, we have to show that for efficient tester, the sensitivity of z bar is low on every element of the domain, every possible data set. So the issue is that even for the independence, the log n thing does not hold for all the possible samples. So there are some sample set which happen with some very small probability that their sensitivity of the algorithm or the sensitivity of the statistic are actually super high on them. What we did was essentially we mapped this bad data sets and mapped them to low sensitivity data set, and essentially run the tester on the new data sets that we received after the mapping. Obviously, it does not give us accurate test result because we are essentially getting our input and change it to whatever we want, but it essentially satisfies the privacy guarantee. And since those bad data sets happen with only a small probability, it does not change the accuracy by a large factor. So as long as it happens with a small probability, we can handle that. Yeah, and in the mapping part, we need to show that there is a coupling. So if we map x's to the yi's, we need to show for every two neighboring data set x and x prime, there is a coupling between yi's such that the distance between yi's remain a constant, and then we can show that the algorithm essentially stays private. So putting all of these pieces together, we get the results that I stated before for testing closeness with unequal size sample independence, and also redriving the result for redriving tighter result for closeness and uniformity in identity testing. And this is end of my talk. If you have questions, please send me an email, and thank you.